Hello, Professor. My name is Marco Schukraf.
My name is Thorben Casper, and we did the CA on the my deck. We decided to do the piano, which is CA number 3, and now we will explain it to you what we've done in the video.
And we will do this in two parts. First, we're going to go through all the functionalities that we have implemented, and we are going to do this while viewing the front panel. And in the second part, we will go through the block diagram and explain in detail how we came to all those solutions.
So let's get into it.
The first task was to extend the keyboard, and we thought about extending it physically at first, but we actually thought it would be way more interesting to be able to access all the octaves like we did it here with this function. Indeed, you can see that we can not only we can choose 4 and 5, but we can also use 1 till 7. For example, at a very low octave, we get a very low frequency sound. And if we choose a higher octave, like 7, we get a very high-pitched sound. So this is about the first task.
The second task was the visualization, so you can see two diagrams at the top. The left one is showing the frequency domain. Oh, this is a very high tone. And the right one is showing the time domain. So you can see that if you hit the different buttons, keys. The third task was to implement different harmonies. You can see it on the right here. The fundamental wave, you can actually key in the amplitudes of the different overtones. So you see the difference if I add a first overtone or if I don't add one. And same for the second and the third overtone. Yeah, that's about the third part. And then we added some additional features on the left.
So now we're going to explain the added features that we implemented. So the first features here on the very left are digital signal processing features. The first feature, we called it the undulative effect, is actually an amplitude modulation of the output. So if we put it at low level, we will hear something like, and if we put it at higher level, we can hear something like. The second effect that we implemented is that we thought that maybe the people didn't want to switch straight away from one octave to the other, but also to do some more fine frequency shifting. And so we shift the whole keyboard just by a smaller frequency, not by the whole octave. This is here implemented in the second effect. For example, if we don't shift it and select octave number 4, we get, and if we shift it to the higher value of 100 Hertz, we get. The other type of functionalities that we implemented is here with a song that you can play and actually you can also play by yourself while the song is playing.
And you can also select the different stereo channels, so you can only use the left loudspeaker, only use the right loudspeaker, or use them both together. Finally, you are also able to change the volume here. Now we are going to explain all the different features we introduced here in the block diagram. So here you can see our actual block diagram. We will start to explain it sequentially from the left to the right. We implemented 3 sub-VIs to give it a clear view, and Marco will start to explain the first part of the block diagram to you.
So I'm first going to explain the left part of the program here. So on the very left here we have the keys of the keyboard. This part of the program will retrieve frequency corresponding to this keyboard. Here are all the frequencies. This frequency will then be passed in this wire. This first sub-VI that we implemented, that we can see here, allows us to switch from one octave to the other. We thought first about doing just a bigger array, but this is not a good solution because an array containing all the frequencies would be very big, and as we are working on an embedded system, this is not a good solution. So we use the fact that from one octave to the other we can multiply by a power of 2 to switch to a higher octave. We decided to put the frequencies of the 4th octave in the array. We did that because the 4th octave is in between the first, is in the middle in between the 1st and the 7th octave, and hence the maximum multiplication we would have to do would be by 2 power 3. Also, doing a multiplication by 2 power n is easy for the processor, as it's just corresponding to a binary shift. Now we will examine the case no key is pressed. So if no key is pressed, the value coming out of this wire here will be -1, and this system here will get an output of 0 in this wire. So this will correspond to a frequency of 0, which will be translated to the generator, and the generator will hence produce a signal that is of frequency 0 and with a DC shift of 0. That is to say that he will just produce a 0 output. Now we will go into the further detail for the first effect, the fine frequency shift. So we know that a fine frequency shift should only be done if the key is pressed. So that's what we'll do by this first part, examining, verifying that a key is pressed. If this is the case, the value of the fine frequency shift will be added here to the frequency that we retrieved from the table and modified with the octave selector and pass it to the generator. We will now go into further detail of the analysis of the function that's called play song for Elise. If I open the sub-VI, we see that we put here in the array all the frequencies corresponding to the notes of the song. We want this device to read each frequency and take it out to bring it to the generator. So it's going to go out here through the wire to the generator. This has to be done one after each other. That means that the index that is brought here to this device has to be a variable increasing. And we achieve this by programming in a while loop where the index I will increase at each cycle by 1, and this I will be transmitted to the sub-VI, and hence we'll be able to read one frequency after the other. We'll also put a timer here so that the song doesn't play too fast. Now Thorben is going to explain the rest of the program.
So in the next part of the block diagram you can see the actual generator which creates the sinusoidal wave you can hear in the end. Therefore our first approach was to only use one generator to create all 4 harmonies, because it saves power in comparison to using 4 generators. But to do this we had the idea to do a frequency shift by using digital signal processing functions, but when we thought over it, we thought that the CPU has to use too much time for this, so the performance is going down. That's the reason why we were looking for another way to implement this. Therefore we looked for an already implemented VI given by LabVIEW, which we couldn't find. So then in the end we decided to finally use 4 generators, which you can see in the sub-VI here. The frequency transferred from the first part of the block diagram to the generator is coming in here and creates the fundamental wave. This input is the frequency input, and for the overtones, for the different harmonies, this frequency is multiplied by 2, 3 or 4 accordingly, and finally it gives you a summation of 4 sinusoidal waves of different frequencies, which is transferred to the output of the sub-VI. So the output of the sub-VI is transferred to this wire. Now I will explain how this signal is actually converted into sound, which you can hear in the end, and how it is transferred to the output. Therefore there are 2 MIDAC assistants which are used, one for acquiring the signal here and one for generating the signal for the output. To achieve different voltages, different volumes, you have this control unit here, and the amplitude modulation, which created the interesting acoustic effect you could hear earlier, is produced by this sinusoidal generator. So this part of the block diagram is responsible for the selection of the channel, either the left or the right, or you can use both. Therefore on this wire you can see an actual combination of the 2 signals, left and right, which can be split up onto 2 wires, and therefore as you have the left channel on this wire and the Y channel on this wire, you can just multiply it by 1 or 0 according to the value of the different buttons. Therefore, in the end, you have on this wire either the left or the right channel or both of them. So for the visualization of the sinusoidal signals, we have two graphical outputs here, one for the time domain and one for the frequency domain. To achieve the frequency domain, we do a fast Fourier transformation by using the spectral measurements expressed VI. And therefore, you achieve a visualization. You have the extension of the keyboard, and you produce some harmonics and additionally some extra features. Finally, that's how our program works. And yeah, I hope you enjoyed our presentation.
Cool.